Howdy. So, we're back now for part three of our investigation into neural networks and how these things function. The last two, we've gone in detail of how individual neurons can do very small scale functions. It's been pretty important to nail that home. I know it's hard to follow sometimes. There's a lot of strange little math to it, but I hope I've illustrated it for you at least the idea that we can simulate artificial neurons that are similar to real world processes, real actual neural processes. Specifically, we covered perceptrons, and these are sort of simplified case of they just either fire or they don't given two inputs. These are really useful for building very simple neural networks, and we demonstrated how they can easily capture all kinds of Boolean functions. You know, as long as it can rearrange its what's the word? Its thresholds and its weights to be able to, you know, cut across the function properly, linear separability. It's able to capture any Boolean function. And any Boolean function or other function it can't capture, you can use the power of strength in numbers to combine perceptrons and handle virtually any mathematical function. We did see how there were some issues with trying to capture. When you're trying to train, you might hit local minimums and maximums and not be able to find the correct solution, which happens here and there. So another key idea here is that the more nodes you have, individual false, pseudo neurons, and the more layers of those neurons you have, the more complexity you can achieve in the system. So you can actually handle more variety of functions, and like I said, they're harder to train those. It's not so straightforward on how to update them, and they might not necessarily converge. So I wanted to kick it up a level here and say, let's look at. Well, okay, wait, sorry. Also to review, there's supervised and unsupervised learning. We looked explicitly at more directly at supervised learning, right? You can train one of these systems given a perfect set of inputs and outputs. So here's an example of the correct solution, right? Kind of like harkening back a little bit to how we did with expert systems, right? We looked at how you could train expert systems based on examples, right? There was a bunch of tennis and rainfall weather stuff, right? And you can train a system using those examples. That's supervised learning. And then the system will take its errors, it'll realize it's wrong, and it will adjust itself based on that. And then there's also unsupervised learning, where you build up networks just by having neurons that happen to fire together become more positively connected or negatively connected, depending on what they're observing, right? So today we're going to look at some more examples of these neural networks and some of the cool things they actually can do. A little bit more of an applied check on how these things scale up to things that are more like human cognition and less like just and or not, etc. Yeah. So, and we'll discuss a little bit about neural information processing in these networks. So let's look first at AlexNet. This one is pretty fascinating. It's a little tricky to explain all of its parts, but I think it's visually fascinating. So this is an unsupervised image classification network. The idea is it's just going to expose it to loads and loads of images, and it knows the category of the image, so it's not, I guess it's not 100% necessarily unsupervised. It has to have some kind of information to be able to train for different categories, right? But by and large, the way that it builds itself is unsupervised. It doesn't say that's a dog and then it gets an error feedback saying no, that's not a dog. It's given something. That object says this is a dog, and it observes it and it trains itself based on that. it looks at 100 million dogs, it looks at 100 million houses, right? And what it's trying to do is pick up on the regularities and the patterns within those systems, within those images rather, not systems, to say what, how do I recognize this? And so in this network, at the very low levels, you have just like edges and very simple textures. And then at higher levels, it's able to combine those edges and simple textures into recognizing shapes that are more recognizable to us. Like it's able to say, there's a node in a high up network that activates when a dog is in the image, and it won't activate when books are in the image, right? Because it's very sensitive to a specific combination of features that create it. So let's look at it a little more. There's a link here too you can use. Go check out this this pattern on its own. So these are it's kind of weird because of the way it's trained. All it's doing is picking up on the small, subtle differences of things. I know there's a lot of weird imagery going on here. That's just fine. It's picking up on some very specific types of patterns, right? And the centrality of the image doesn't matter so much, but it's the idea is if I hand this image to one of these to this network, for instance, the house neuron. Now, by the way, the network on the right is just to sort of illustrate that there's different patterns going on. One of these might or might not be the house neuron in the network. But the point is that at this high level, there is a neuron that is most sensitive, it's most active when something that looks like a house is available. And there's a way you can sort of reverse engineer, well, shoot, what's the thing that would be most, is the exact image that would be most activated, that would most activate this neuron. And that's why this image that we get here is a little bit, you can kind of tell it's a house. It's got a lot of stuff poking out the top, room for a lot of different kinds of roofs. It's got, there's a lot of features on the face of the house. It's got that triangle shape, and so I hope it's clear that this is like, this neuron is most active with this really weird abstract image, but that also means that it's going to be quite active when real houses show up. Unlike, say, the dog snouts neuron. The dog snouts neuron is trained on a much more specific individual pattern here, and you can see it right now. You can see that dog snout, right? It looks kind of like, a little like a wolf, but it's a dog. You can even see an eye in there, and if you notice, there's another whole network, or sub node down here that's most sensitive to dog eyes. So almost certainly that dog eyes network and sub network and node is helping to activate dog snouts. Dog snouts is also seeing the curves and edges and all that stuff. So so if you feed this image of this more or less actual dog, it's very smeary and blurry and interesting, but it's a more or less a dog. We can recognize it ourselves. This is the image that will most activate the dog snouts neuron in the AlexNet network. And once again, that means that similar images that contain a dog snout will also activate this network. So this is pretty wild. I mean, looking at it top to bottom, bottom to top, you see it starts with these really simple, fine-grained, some sort of like, at the very bottom level, a little bit more organic looking patterns, sort of zebra-esque. A little bit more ridgy things, some swirls, some dots, some polka dots. And you can picture how maybe those kind of filter together. If, say, you combine some of the swirls, some of the concentric circles, and some of the, the things that look a little more like fur, you can see how those might combine into the dog eyes one. That's the second column, third row down. You can see how that particular neuron is being activated by things that are related to it. If I see a concentric circle, some wavy patterns next to it, and some kind of fur-like like structure, I can go ahead and say that's probably a dog eye, right? My dog eye neuron can light up and show, hey, I think there's a dog eye here. So that's why this is a classification network. So I hope that this is fairly clear. It's an interesting phenomenon here. Um, this is AlexNet. I mean, it's designed to look at a whole wide array of different natural images and develop a network that has different subnodes that are sensitive to different phenomena. And it's composed of those so the higher level concepts like library or house or dog snout are composed of activations from the lower level layers. And the cool thing about AlexNet is that it seems to have built up a bit of a what you might call a visual vocabulary. It can you can use it on images it's never seen, and it can give, you know, as opposed to the verbal vocabulary of here is a this is a dog. You can actually see sort of the visual vocabulary. Going back to it briefly, you see the swirls and circles are sort of an important visual concept, right? Those are a subcategory of something that's more specific. We also can see, for instance, just because this is such, it's so cool. Look at the first column, third row. That's detects bookshelves. You kind of get it, right? Things that are lined up with a flat bottom but different edges, different shapes and sizes on the top. You can see how that's probably using that more sort of strange shaped thing in a third column, fourth row. It's almost certainly making use of these sort of rigid, squarish, specifically this array of sharp edges, right, to use to create bookshelves. So, yeah, AlexNet just observes information in the world, and it builds up this network of, you can consider them very similar nodes to what we've already covered, very perceptron-like. Some of them could work better with not that immediate like binary on and off, but more of like a gradient for color and things like that. But yeah, so that's AlexNet. AlexNet is a system that can categorize natural images. Let's move to a different kind of subdomain here. We can also talk about handwriting. So, handwriting generation. Graves, 2013 paper on this project. The idea is that this network is able to observe handwriting alongside the text. So it's supervised in the sense that it's able to have the actual text that it understands, and it's able to read written text to sort of create a mapping between the two. It sees somebody's handwriting, and it does its best to parse that into text. The cool thing about this handwriting generation network is that it works both directions. So by training it up to say, hey, here's a bunch of scribbled text, and here's some the actual text of that. Here's the actual, the string, the data associated with it. You can both classify handwriting to say, oh, I see what that is, recognize it. Post offices actually use this quite a lot now. You might not have thought of that, but post offices use neural network pattern matching to help say, oh God, this person really scribbled this on, what is it? So that you don't have to have a human being operating on it at all times. Also might be why sometimes it goes to the wrong place, but who knows. But the other direction, the cool part is that you can also take text and have it generate it backwards, generate it into handwriting. So let's look at this example. Cogito ergo sum, carpe diem, other Latin nonsense. This is the text I fed into the handwriting generator network. And what it's done is it has generated handwriting that looks pretty dang good because it was trained so well with so much handwriting and so much, confirmation of what the handwriting said. It's able to hand back something that looks very close to human writing. You can see it misses a few things. It's a little bit funky. So, for instance, carpe diem, that dotless I, that's a little strange. But also we've got down in the third line, cogito ergo sum, carpe diem. Other some weird stuff's happening with the H, the Latin, the A is all kinds of messed up, but it works. These look like a lot of different people may have written this same sentence out. It's creating something that it's creating patterns that are very human-like, just because it's been trained on observing human patterns. Very cool stuff. We can also look at a little bit different, same vein, but a little bit different phenomenon. So it's like handwriting generation, but instead of those pixel images, it's doing a one-dimensional wave. So the sound waves. It's able to process, to hear sounds, and then output, or rather, it's able to be trained on voice, and it's given the text, right? Same thing as the handwriting, it's just in a audio format instead of a visual format. So now it's able to classify different text into, or speech into text, or text into speech. You've used this before. Whenever you talk to Siri or OK Google, right? That's the same phenomenon. Alexa, right? So to make that a little more clear, the images that the handwriting network was looking at were these dot matrix, right? It's a bunch of white dots and black dots, more or less. That's how printing works. That's how you can recognize what's on a page, right? It's just visual patterns. This is more, like I said, one-dimensional patterns. If you've ever seen a waveform of a voice, an audio waveform like this, it's a lot of information moving around. We can zoom in and really show what that looks like. It's a lot of data moving up and down quite rapidly. It's fluctuating. How active should the speaker be to output this information? Which is cool because, again, instead of 2D pixel data, I'm just giving it this one-dimensional audio data. Like what is the pattern, right? That's the beautiful thing about these networks, is that if you can get it into a data format, you can feed it into the network. You can train any of these networks on anything that is a set of numerical data. So let's look a little bit more about what WaveNet is doing. So it feeds it. What it does is it's trying to predict the next sample, the next data point in that line. So it's trying to, if I'm going I'm having this audio sound, I'm going up, right, up in my tone. The frequency, how quickly up and down that audio moves in the waveform is going to get closer and closer together, right? Higher frequency is higher audio experience, right? Higher pitch. So if WaveNet was going to try to predict that, it would become able. It looks at. Sorry, it's a little funky. So it looks at a little subset of the data, and it tries to figure out what's the next piece of information that's going to come. And again, it's doing it at a very fast rate. We're talking about things that don't even resemble human audio, but because it's predicting 1/16,000th of a second of audio at a time, it just does one at a time. So what the network is doing is it tries to predict the next piece of audio, and then it uses that to predict the next one. Uses that to predict the next one. It has this sort of window, this moving window of I'm trying to create a waveform out of the previous audio that was fed to me. It's a little bit not super intuitive, but this is a little bit more about how these systems work. Information propagates from the input. The network is trained to be able to make that proper output prediction, and then it's able to both classify and generate sound. So let's look at some examples here. Um, Google has two methods of generating human speech. They have concatenative, parametric, uh, and then WaveNet has its own method. So concatenative. So this is a little weird. I'm not perfectly familiar with it. I think what it's saying is that Google's methods, they have they are typically built in a sort of mathematical way to try and predict information based on math laws, right? Parametric. I feed it algorithmic math functions, and it tries to handle it. WaveNet is an actual neural network, right? So what it's doing is it's actually trying to, it uses the power of having mass distributed small networks, small nodes all over this network to really pick up on the nuances of human speech that these other sort of more straight up mathematical approaches don't quite get, right? If this harkens back a little bit to our discussions of analytical models, right? Mathematical models that predict outcomes, or computational models that actually generate the behavior, you see that WaveNet is more in that generative model area, whereas these other ones are more in the analytical area. So it makes sense that they would be rated a little bit more close to human speech because they're doing a lot. They're capturing a lot more of the nuances. So let's hit play on some of these sounds.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Right? This is familiar. We've all screwed around with Google Voice stuff here and there, and this is what it can output using that method. Now they also have the parametric method.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Bubbly audio quality to it. You can see why that's rated a little bit less. It still works. It still does a pretty good job of sounding fairly human, but it's a little bit wobbly, kind of robot-y. Now let's hear WaveNet.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
All these differences are subtle too. I mean, it's not like people are rating the parametric model as a 0 on its humanness. I think the humanness is out of 5. But WaveNet captures more of the subtleties, the small pauses, the little inflectional differences, that kind of stuff. Things that we're evidently able to pick up on. So yeah, this is another way that we have applied neural networks to an interesting problem, right? Okay, let's move on to another category of these neural nets. There's a pretty cool trick you can pull with neural nets. Because they're so good, and because they're so good at learning, you can pair them up to try and train against each other, which is a pretty cool concept. So a trick that they can pull it's called creating generative adversarial networks. And the best example, or the best metaphor for this is it's like you have created a forgery artist and a detective. The one is trying to create the best image, the best fake image it can. You know, it's doing similar things to AlexNet, right? It observes the world, it takes in a lot of information, and it's built up this whole thing. But then it also has the ability to dump those images back out in as realistic a way as possible, right? The detective, on the other hand, its whole job is to try and detect, is this thing accurate or not? Is this thing a real image or not? Are there enough weird little broken things in this image that I can say, yes, this is fake, or no, I'm totally fooled? And you just pit them against each other. So the generator, so we have the knowledge. We know when an image is real or not. The generator's goal is to create the images, and the discriminator's goal is to identify if that image is real or not. So the generator gets rewarded. Its system gets updated with positive weightings if it actually succeeds in fooling the discriminator, and the discriminator is rewarded when it spots a fake. So we know, we outside, this is certainly supervised, we know outside whether or not an image that we hand to the discriminator is a fake. So under those conditions, we have these two systems that they both start terrible, right? The one is creating garbage images, and the other one is terrible at discriminating them. But because they're both getting rewarded for the behavior they're generating, they're able to really push each other forward. So you don't have to have quite so good of a system in place for specifically training the generator. You can just create a discriminator too that is able to compel the other forward. They both grow by competition, right? So let's look at some things that this system has created. So here are some things. At first glance, these are pretty dang good. These look real, but there's some funny things going on. So these images have all been created by a generative adversarial network, a pair of adversaries that are trying to trick each other, and they've gotten really close. But at first glance, these are good, right? It's pretty astounding at a moment's notice how good they are. But you start to look in at the details and you see some weird stuff. For instance, that dog, he's got the husky, the whatever we got up here, the upper left. That's too many legs, huh? It's got some weird stuff going on with its legs. It's got sort of a strange middle leg coming out of its chest, and its back legs are sort of missing. This mushroom, it's all right, but it seems to have some eyeballs. Not clear. It's a little bit lower res than it's easy to see. The teacup over there has some, it's kind of malformed. I don't know that teacup would sit upright properly, not necessarily. That rocket ship is almost certainly made of lipstick. And then other things, I don't know, the fountain. There's some weird stuff going on with the gravity of how that left jet is sort of shooting up into the air and then moving straight left for a minute. So you see how it has not completely conquered the visual domain, but it's done a pretty good job because they've both spurred each other forward to this point of being able to really produce something that is confusable with real world. Also, here's a little exercise. Which one of these faces is real? I'll give you a moment. Start looking at the details. They're both fake. So these were both generated by these generative adversarial networks, and you can see it pretty. It's tough to tell with the guy. His eyes look a little dead, but it's not totally clear that it's wrong. You see some blurring around the edges, but it's done pretty good to create this totally fictional human. Now, the gal, on the other hand, there's some weird stuff happening with her ear, that's for sure. And her canine it's a little too long, huh? It's not great. Not great how that works. But it's done okay with the eyes on both of these people. It's done fine. And that's the wild thing. These systems are pretty dang good at generating images at this point. So we'll keep moving. There's also a realm of understanding how one of these systems can be used, sort of more in an applied way, for some interesting artistic way of given. So a system that has been trained on images with particular regions defined, right? In this case, at the base case of this little system, we're seeing the bottom region is water, and the top region is sky. In this little like left hand panel, that's like the input. The output is in the right hand panel, and what it's showing is it's able to kind of summon up an image whose regions are defined like that. But it's generating this image. It's very similar to these. In fact, I believe it's run at the heart by a generative adversarial network. So let's watch what happens if we change these input regions. This guy's drawing rock here. It just generates new rock, and it also generates. You can see a little bit of the way the rock is actually sitting in the water, sort of, right? It's able to understand both the region, the size of that region, and sort of the way that region might interact with the other regions. The sky, the rock doesn't interact much with, because that's true of real life. You just have a rock and a sky; they don't blend together at all. But as it sits in the water, we even see the reflections. We know that water will reflect things that are above it. This is wild. We're seeing the ability for generative adversarial networks to capture some really nuanced things about the way that vision works in the real world, and it's doing so in this extremely generative way. It's borderline creative. We're seeing the edges of how one of these systems could be involved in creative processes, or even potentially one day create its own creative processes. It's very cool stuff. So generative adversarial networks are this way that you can sort of bootstrap these two guys together and say, "Hey, go off, run into the wild, and try to beat each other." That back and forth creates this really cool upward spiral of training each other to new and more interesting different applications. So, and more realistic scenarios. The beauty of that being, you don't really need a human to intervene very much here. You don't need somebody who's able to, give it a lot of examples. They can just go and try to fool each other continuously, as fast as a program, as a computer system, a large scale computer network could handle. So, so I hope this has been pretty cool, just to see all these examples of how some of this works. And in fact, a lot of these are kind of outdated at this point. There's so much power in the world, and there's so many different groups using neural networks now. I mean, it's big out there in the world. Some really cool stuff. So I hope you now see a little bit more about how they work. And so we saw a little bit about how we can classify images, handwriting, and sound, and then double back and actually generate images, handwriting, and sound from those same kinds of networks. And then this powerful way of learning by way of competition, right? Very cool stuff. But we want to bring it back to a core theoretical question of the course, right? How does all this fit together with the overall concept of information processing, right? If we are still in the world of, hey, information processing is key to how human brains work, and it's also extremely useful, but we don't necessarily subscribe to the physical symbol system hypothesis. We're saying that neural networks are the specific situation. So how do we look at information processing in the neural network world? So they are clearly algorithmic. I hope that's clear to you, because it's all just math, adding things together, summing them up, editing that math, changing the parameters, all that stuff. It's just these, and the great thing is that it has rules for both transmitting information and learning, right? We have the delta rule, helps to understand how to update the perceptron, and just the way the perceptron works, right, for how it transmits information. So that's cool. But here's the thing: physical symbol systems are algorithmic, of course. We went through that in great detail, But they're treating it as this very cleanly described algorithm that is very it's very neat, right? Neat and tidy. There are abstract things called symbols. They move around in a very clean way, right? I transform one symbol into another. The language analogy that all of it is working like language. There are rules for how to transform one sentence into a different sentence that has the same meaning, that kind of stuff. The cool thing about neural network algorithms is they are super general. They don't subscribe to a very specific, neat and tidy set of rules for how the system must be defined. Really, all they're saying is, hey, I'm not looking at the high level, I'm looking at the very low level processes. I'm anchoring myself to the most accurate physical simulation I can of a single neuron, and then seeing what emerges from the world from there. So neural networks don't use the abstract concept of representations, and that is semantic symbols that we've seen before. So representations, we should talk a little bit about that. How do I conceive of my grandma? You may have heard of this a little bit before, but think about your grandma. If you knew your grandma, but otherwise somebody close to you at some point in your life, but somebody who you may not see that often. Sure. So how should we conceive of grandma? In the physical symbol system world, it might be a symbol that is directed and attached to a set of concepts that are all connected to one another, and memories and all that stuff. And that's good. That's fine. But how do we conceive of that, the concept of grandma in the neural network take on all of this? So the representation that we use to access grandma in a neural network world isn't a single symbol. It's this sort of overall pattern of activation of the network. Similar in concept to the dog snouts that we saw earlier, the houses, right? There is a particular pattern of activation in your brain that makes you, remember and conceive of your grandma. How is that exactly represented? The pattern of activation? That's in the weights. It's in the threshold. It's in the learned knowledge. And you can really represent very complex ideas as these multiple overlapping patterns, as opposed to the more physical symbol system approach of unique, very specific symbols. So continuing on with grandma, you may have heard of the grandmother neuron. This is an interesting little, once again, a thought experiment to say, where does grandma live inside your brain, right? Where exactly does she live? How is she represented in your brain? Is there a single node? Is there a single grandmother neuron responsible for helping to recognize her? Or is it maybe a small network? Maybe it's distributed across the entire brain. And this is sort of a goofy image of, the concept is there one particular spot where I keep track of all these different concepts? The Jennifer Aniston neuron, if any of you can remember who she is. The dodecahedron neuron. The grandmother neuron. The grandmother, the neuron pointing to the concept of the grandmother neuron, right? So this is an interesting thought experiment because it shows that it's a little bit silly to consider, okay, there must be individual neurons, but the trouble, and that would be quite nice for the physical symbol system world, because then we can point to one exact spot where, that symbol, that lives there. And that's not totally wrong, right? A lot of times, everything is a little bit in between, right? It's not totally wrong that there are individual cells that are really, really selective, right? But it's an interesting element to consider that there's very little evidence that any one neuron only activates for one thing. So more likely is, it doesn't matter where grandma lives, as long as the overall network is behaving in a way that distinguishes her, understands her, can communicate with her, can remember her, whatever function we need to operate. We don't need an individual single spot where a very clean representation of grandma lives. What we need is to understand the more dynamic, kind of broader patterns that might give rise to our understanding of grandma. So, getting back to the concept then, neural networks and representations. So neural networks have what you might call fuzzy representation. It's all overlapping patterns. They're all kind of laying on top of one another. They might use different subsets of the same patterns, all that kind of stuff. Very much like the AlexNet, right? We have DogNose is composed of lots of subnetworks, right? So it's really hard to construct in this world a very distinct, specific set of, say, in the language of thought model, beliefs, desires, and intentions, right? That doesn't mean that there's no such thing, but it means that it's hard to pinpoint the very clean definition of those things. So, but the powerful thing about neural networks is that even though they don't really do that, they can still solve these crazy complex problems, right? All the ones that we saw today. So they don't need a physical symbol system approach to really tackle some of the really most interesting human problems we've got. So, to sum up more this whole idea about neural networks, they are this kind of this powerful alternative to physical symbol systems in terms of processing information in the brain. They are governed by these very simple rules. The neuron, how the neuron works, how they influence one another, how they change the activation of other nearby neurons, and then also we've seen how they can perform extremely simple information processes like Boolean operations, simple math, very basic edge detection, pattern recognition type things, up through the very edges of creativity and mental imagery and creating images that are really high fidelity and being able to process the world in more human ways than we might have expected. So, I think next time we're going to look at some more applications of neural networks, but more in sort of the scientific way as opposed to this like cool toys way. And that's not a fair characterization. These are amazing tools that have been built, and they're all built on science. But we'll look more a bit like experimental studies of how you can apply neural networks to these things. So, thank you. Take care. I'll see you soon.